So I'm Jiheong Kang. So as the Professor John mentioned, I'm trying to deliver the message on the about the self-healing soft electronics from the development of the materials to the how we can fabricate the devices. So let me briefly introduce myself. So I got the PhD from the Professor Takujo Aida at the University of Tokyo. So at that time, I was more focusing on the fundamental supramolecular chemistry. I synthesize the molecule and look at their self-assembly behavior in the solution and the solid state. So after getting the PhD, I moved to the Stanford University, and I did work with the Professor Jenan Bao. At that time, I taking advantage of my fundamental supramolecular chemistry to develop the new self-healing materials and apply to the stretchable electronics. And last year, I just started my independent career at the KAIST. So today, so maybe I will focus on the my work, what I did in the Stanford University. So my initial motivation at the Stanford University was how we can make the high resistance to the mechanical stress. So basically, this kind of the external mechanical stress is kind of the origin for the breakdown of the materials or the devices. So basically, I was more focusing on the soft electronics, how we can improve the their durability and also the resistance to the external mechanical stress. So basically, there are so many work on the how we can develop the soft electronics. However, consider their fabrication and approach is we cannot believe that they can have the high resistance to the external mechanical stress. So my motivation is how we can manage the mechanical stress from the external stimuli. So I would like to develop the some self-healing materials to improve the durability and also the long-term stability of the stretchable electronics. So today my talk I will focusing on the three topics. First one is how we can fabricate the self-healing elastomer and how we can fabricate the self-healing conductive materials and also how we can apply this material as interface materials for the some new opportunity in the stretchable electronics. So first topic is the self-healing elastomer. So first I would like to explain what is the self-healing materials and what is the challenge point in the self-healing materials.
In your screen at the bottom right corner, yeah, there is something covered. Thank you.
Is it fine?
Yeah, it's fine now.
So here is the most simplified polymer network for the elastomer. So there's a flexible polymer chain and also they're cross-linked by the chemical bond or the some physical interactions. So after, if we apply the some mechanical stimuli or the some extreme stress, some of the bond should be broken or some physical interaction will be suppressed and they will lose the mechanical strength. So in contrast, the self-healing polymer network, even though we apply the mechanical stress and the some of bonds are broken like this, they autonomously reform their bond and can restore their mechanical properties. So this is the basic principle of the self-healable polymer network. So however, difficulty is the self-healing material is their poor mechanical properties because they are based on the very low TG of the polymer chain and they are solely based on the dynamic bond. So they conventionally show this kind of significant creep and also the plastic deformation under the high strain. So simply speaking, they are more like gum-like properties rather than the fully elastic type of the elastomer. So we need to overcome their mechanical properties in order to apply to the stretchable electronics or the soft electronics. So my motivation, so my approach is quite simple. I just simply imagine that if we can incorporate the two kind of the bond with the different mechanical, so bond strengths. So maybe two bond play a role as a very independent behavior. One is a very strong bond to impart the some elasticity, and the other bond as a weak bond show the some very fast energy dissipation to promote the self-healing properties. So of course, there are a lot of the lists as some dynamic bond for the self-healing system. So I was mainly focusing on the more hydrogen bonding based self-healing system because it is more simple and easily synthesize the various type of the some molecules. So again, so my supramolecular, self-healable polymer network, they're composed of the two bonds. One is a strong bond and the other one is a weak bond. So strong bond and weak bond, they are basically show the very similar molecular structure. They both have the two urea group at the end, but different things is their center part of the molecular structure. So more polymer design is like this. So we have the flexible polymer chain based on the PDMS to impart the low TG and also the flexibility and the stretchability. And one is the first hydrogen unit here. So this is two urea group. Because of their symmetric structure and the rigid structure of this center part, they can form the four hydrogen bond at the same time in the very cooperative manner. On the other hand, this isopropyl unit base, because of their flipping effect and the steric hindrance of this methyl group, so they cannot form the four hydrogen bond at the same time. They more follow the anti-cooperative hydrogen bonding interactions. So basically, because of this kind of different behavior of the forming the hydrogen bonding, they can show the very different bond strengths. Basically, because of the multivalent effect, their bond strength is the difference more than the four times. So then how we can imagine how they can form such kind of networks. So in order to prove their structure, we perform the NMR experiment and also the viscosity measurement. So actually, if you want to make the film, first we need to dissolve the polymer in the solvent. At the low concentration, they should be highly dispersed and that there's no particular physical interaction between the polymer chains. But we found that at the certain concentration, only a strong bond starts to form the bond at this concentration, and weak bond is highly dispersed. And based on this pre-crystalline structure, after fully evaporation of the solvent, they eventually make this kind of it's a very interesting self-healable network with the two kind of the bonds. So here's the three important mechanical properties. One is the high stretchability, and the other one is the very high toughness. And the last one is their self-healing ability even on the water. And also that this robust material also show the very nice dielectric properties. So they are readily for application in the some electronic applications. And also because of their fracture toughness, it is a very good main carrier material for the bioimplanted application. So if you want to implant some electronic devices to the tissue, it is inevitable to do the suturing process. So most of the PDMS materials, because of the low fracture toughness, during the suturing, most of the substrate will be broken. However, due to the very nice fracture toughness of our materials, even the very harsh suturing process, still they can maintain their structure and keep the nice mechanical properties. So this is a summary of the first topic. I showed how we can toughening the conventional self-healable polymer network and show the very nice mechanical properties. So let me move to the second part. Before going to the second part, I would like to show the some recent our advance in the self-healing materials. So as you may know, the most of the self-healing materials, they are based on the non-covalent bond, so they show the very bad thermal stability. But we found that if we can promote the self-assembly of the such kind of the dynamic bond, we can dramatically improve the temperature stability. So even with the same molecular design, by contouring the overall length of the polymer, we found that we can promote the fiber structure in the polymer film with the dynamic bond. Then we found that even under the 100 degrees C at the relatively high temperature, still this nanostructure can be maintained and show the really nice mechanical properties. So this is a fiber structure in the by the AFM. So as you can see, this dynamic cross-linkers start to form the very nice 1D structure and dramatically change their mechanical behaviors. And also recently we developed some very nice actuator based on this supramolecular polymerization method. So we make the very tough material based on the supermarket polymerization, then it shows the really nice actuating properties under the high temperature. So with the very small amount of the film, they can actuate the very heavy object like this. So then I would like to move to the second part about the how we can make the self-healing conductive materials. So basically, most easiest way to make the conductive material is just adding the conductive component into the polymer matrix. So our initial motivation was that we are very curious if we embed this kind of the 1D nanowire based conductive nano network, whether they can change their behaviors depending on the embedding polymer matrix. So we embed this CNT or silver nanowire based nano network into the fully cross-linked the elastomer and the self-healable polymer matrix and also the gum-like polymer matrix. And we found with a very big surprise that upon embedding this nano network into the self-healable polymer matrix, we found that this nano network also can start to have the very dynamic properties and that they can reconstruct their nano network under the mechanical stress. So here's a video. So we prepare the electrode and we start to scratch with the razor blade. So initially, if you scratch with a very low power, you can see there's no change of light intensity. So we start to increase the power of the scratch to fully damage the surface. So in the case, at this moment, it's a very unstable, but they start to restore their bright intensity, meaning that they can reconstruct their network and restore the electrical properties. To fully investigate what's happening here, so we perform the more quantitative analysis. So we measure the forces of the scratching. We increase up to the 4 Newton. So after remove the laser blade, you can see the very rapid recovery of the resistance at this first step. So it is more related to the physical contact between the damaged surface. But more important thing is over the time, you can see that there's significant resistance decrease over the time, meaning that they are continuously reconstruct their nano network and restore their electrical properties. To visualize what's happening here, we perform the SEM measurement. So upon the damage, initially because of their insulating properties, we couldn't visualize the nano network in this damaged area. But after the 12 hours they start to reform the wall of the network and going to be a very conductive. Then we start to visualize this damaged interface, meaning that they're truly dynamically reconstruct their network over the time. And in order to confirm their mechanical healing, we fully cut their electrode and put together. And after the 3 hours, we found that upon the stretching, still they can maintain their mechanical properties and also the electrical properties as well. So now we have the very nice insulating layer and also the very nice conductive materials. And because of their mechanical robustness, so we enable to fabricate this kind of the integrated self-healable electronic scheme with the multifunctionalities. So they compose of the strain sensor and the ECG sensor and the display. So all of the components are fully self-healable system. So even after damage, they can restore the sensing ability and also their light emitting properties. And also this approach is not limited to the 1D nano networks, so they can also apply to the 2D system. So even with the silver flake systems too, they can show the very dynamic behavior. So we found a very interesting electrical self-boosting event inside of the polymer matrix. So now I'd like to move to the last part about the how we can use the self-healing materials in the stretchable electronics as the interface materials. So initially, my starting point is I would like to make the stretchable semiconductor. So most of the semiconducting materials are quite brittle, even the organic materials. So basically, the conjugated polymer have received a great attention for the stretchable semiconductor because of their semi-crystalline behaviors. But even with the conjugated polymer, they easily show some micro crack formation at the 20% strain. So, so I would like to improve their stretchability of their conjugated polymer with the different way. So if you look at the fracture mechanics of polymer thin film, so we need to consider the two situations. So one is just a freestanding thin film, and the other one is thin film on the elastic substrate. So in the case of the freestanding thin film, because of some stress localization effect, they easily form the fracture at the very smaller strain. But on the elastic substrate, so substrate can retard the stress localization effect. Somehow they can avoid the complete fracture. Instead, they form this kind of the micro crack formation. So in the case of the freestanding situation, they are more related to their intrinsic material properties. However, on the elastic substrate, we need to consider the interface properties as well. So I think in the case of the elastic substrate, we need to also consider the material parameter and also the interface parameter. So however, the most of studies so far is that they are more related to the material properties engineering. By incorporation of some elastomer metrics or some introduce the conjugation breaker and or introducing some hydrogen bonding conjugation breaker or making the nano confinement effect inside the polyometrics, they dramatically improve the stretchability of the semiconducting materials. So however, so far there's no report about how we can engineering the interface and how they can affect the behavior of the semiconductor polymer thin films fracture mechanics. So I just focus on how we can improve the interface parameter in the stretch of electronic system and see how they can change the fracture mechanic behavior of the semiconductor polymer film. So here's a scheme that I make the interface very tough interface with the self-healable properties. So basically, I synthesize the new interface material. They composed of the two components. One is self-healable polyometrics, and the other one is an interface cross-linker to promote the nice cross-linking between the two different polymer surface. So one is a self-healing polyometrics, and the other one is based on the Poflolo-Penny-Ajay cross-linker base. So they have the two cross-linker to make the cross-linking between the two surface, and also they have the hydrogen bonding unit to promote the nice topological interaction with the self-healable polyometrics. So basic principle to evolution of the tough interface like this. So polymer film, if there's a different surface properties, they cannot be entangled and they trying to separate, so they show the very poor adhesion. So my principle is in order to make the topological adhesion between the two surfaces, just modify the polymer film with the some certain non-common interaction. So based on the surface modifier, I fully change the surface properties of the polymer film, and this modified surface properties are identical to the secondary circular polyometrics. And because of the very nice hydrogen bonding interaction, the secondary polymers start to stitch into this surface and induce this nice bilayer structure with the tough interface. So basic principle is the topological adhesion and also the efficient energy dissipation by the self-healing polyometrics. So we can make the really nice tough interface between the various polymer surface. So based on that, we start to look at the how this interface can modulate the fracture mechanics of the polymer thin film. So we start to try with the various kind of semiconducting materials. So if you simply laminate the various kind of semiconducting polymer onto the PDMS substrate, as you can see at the 50% strain, there are a lot of the micro crack formation. But surprisingly, we found that when we introduce the tough interface, they couldn't show the any crack formation even at the 100%. So meaning that this our tough interface can dramatically delay the crack initiation and the crack propagation in the semiconductor polymer film. So the mechanism will be like this. So initially, if you apply the tensile strain, then there's a generation of the shear stress like this. And this shear stress will be localized into the defect of the interface between the semiconductor film and the substrate. So however, if you have the very tough interface, we can avoid the delamination issue and also the relax this shear stress, so we can avoid the crack formation and the propagation by this mechanism. Then based on this tough interface, we found the very two important features. First one is the exceptional thermal stability. So basically, if you have the two layers and if they have the different thermal expansion coefficient at the high temperature, they start to make the more defect between the interface. So this is at the room temperature. After heating to the 100 degrees C and cooling down, then you can see there's a significant increment of the crack density, meaning that their interface getting worse and worse. So however, with our interface, because of their very nice dynamic nature of the material, so we can see the very nice thermal stability. There's no change, no formation of the crack. And second feature is the cyclic durability. So if you have the plastic film as the semiconductor and the substrate with the elastomer, so basically they have the very different their cycling mechanical behaviors. So during the cyclic stability, we see the very instability. So this is the first cycle. After the 100% with the 50 cycle, you can see there's some merge of the some many cracks, meaning that because of the difference of the cycling mechanical behaviors, it affect their cyclic durability. So however, but our interface, so they have the some adaptive properties, so they can compensate their different residual strain issue by intrinsically form this kind of wrinkle formation. So based on the wrinkle formation, they can stabilize the system, so we can improve their cyclic durability. And based on this material, we allow us to fabricate the fully stretchable organic transistor by using our interface as a dielectric. So based on this approach, you can see up to the 100%, we can see the very nice transfer curve. But without the tough interface, you can see the significant drop of their current level because of the crack formation. Meaning that truly our approach is quite useful to fabricate stretchable organic devices. And actually our devices, our approach is quite general, so they can apply to the various polymer film, even the PSS and also some gold layer. So this is maybe new paradigm shift in the engineering of the stretchable electronics. So far I developed some new self-healing soft material and applied to the stretchable electronics as a conductor or semiconductor or the sensor. But after coming to the KAIST, I start to make some new generation of the self-healing soft electronics because the current generation of the self-healing materials still have a lot of the problem in terms of the mechanical properties and also the electrical properties. So recently we found a very interesting behavior in the elastomer and also some conductor. So concerning time limitation, I will just briefly mention of our recent advance in the liquid metal particles network. So basically, we trying to make the purely liquid metal based stretchable conductor because of their extremely deformability. But actually, because of liquid behavior, it's difficult to apply to the some stretchable PCB or stretchable electronics. But recently, we found a very interesting synthetic method. So by making the some nanoparticles, the liquid metal particles in between the pristine liquid metal particles and just bridge. So we call this is a liquid metal particle network. So conventionally, if you mix the liquid metal particle in the polymer matrix, you can see because of surface tension, they couldn't form some percolation network. So in order to make the percolation, we need to apply the mechanical stress to break the rupture of some liquid metal particle and leak the liquid metals. But we found that if we make some new liquid metal particles in between these two particles, we can make the very nice percolation pathway with the very high electrical conductivity. And this resultant network showed the really negligible resistance change up to the 500% strain, and also they extremely show the very nice cyclic durability, more than the 1,000 or 15,000. So, and all this method is quite general, not only applied to the some particular polymer matrix, we can apply the this synthesis into the silicon elastomer, SABS, or polyurethane, even in the hydrogel, or even in the very hard epoxy system. So based on this, we fabricate a very nice conductive line with the very nice adhesion with the electronic chip. So we allow it enable to make the really multi-layer, stretchable, and also self-healable printed circuit board with the very high density. So this is the end of my talk. So I'd like to thank the Bao group member and also my group member and also the funding source. So thank you for listening, and I'm happy to answer any question from the audience. Thank you.
Okay, thank you very much. Actually, there is one question from Mr. Hyun-Sung Kim. Can you see the question?
Just a moment. Yeah, I can see the question.
Yeah, maybe we can have one or two questions. So yeah.
So first question is it impossible or thermodynamically unfavorable that the hydrogen bond unit 1 makes the bond with that hydrogen bond unit 2? So basically, in the principle, hydrogen bonding unit 1 also can form the hydrogen bonding with the unit 2. Basically, it is a kind of self-sorting event, even though we mix the 1-to-1 interaction is much stronger. So they have the some recognition to form the hydrogen bond. So even though we mix, they can separately find their partner. So this is the answer for the first question. And the second question is, how can we confirm that the hydrogen bonding are made or not? So basically, based on the FTIR, we can confirm the hydrogen bonding, because upon formation of hydrogen bond, there is a clear shift in the NH vibration or the CO vibration. So final question is, do semiconducting polymer have thermally activated behavior like other semiconductors such as silicon? So it's very different. So organic semiconductive polymers are more related to the hopping mechanism. So they're much better at the high temperature. It's a very different behavior.
Okay.
I have a question.
Yeah. Hi, Xiaodong.
Very nice talk.
Thank you.
Okay, so I really like your cell healing part. So your last part you talk about, you come out integrated device, right?
Yeah.
So how's the performance going on now? Because I didn't see the performance. How is performance compared with inorganic or other kind of current state device?
So you mean related to the semiconductive polymer or just a liquid metal system?
The last part, you talk about one integration device, you just say submitted. I just kind of curiously how performance looks like.
So recently we fabricated the stretchable PCB, and actually they're much better, because I would like to say they show the really high electrical conductivity, and also that they show the really low resistance chain under the stretching, and also the very higher strength. But what I like to highlight in this system is their adhesion with the other electronic components. So recently there are a lot of stretchable conductors show the really nice properties. To once we integrate with the other electronic chips or some stretchable sensor, under the stretching they are very unstable. But our system is show the very nice mechanical property and it's a very tough adhesion with the other electronic component. So even under the 500 strain, there's no change of the electrical performance. So therefore, we would like to highlight to the more stretchable PCB rather than the simple stretchable conductor.